So just to start, even if we do not yet have the presentation, so I will present the activity of Quantum 2.0 at Links, which is one of the five strategic domains that have been discussed last year for the research activities of Links. So it includes people from many in the order of importance in terms of number of people, people from Nokia Bell Labs, from Inria, but also from Telecom Sud Paris. And a bit also Sébastien from Sorbonne University, there was some discussion about distributed system and the quantum version of distributed systems and algorithms. So yeah, this one, yeah, là tu peux passer un écran. So you are here, you have all the, but it's not yet shared.
C'est bien partagé.
OK. Ah, il faut le mettre en plein écran. Vous c'est que pour faire avancer, ça sera avec les flèches, je suppose. Là, l'icône là. Voilà, parfait. Merci. Donc, just to test. Yeah, it's okay, it's okay. So as you see, there are many people from Nokia, Bell Labs, Telecom Sud Paris, Sébastien from Sorbonne also. I see that I miss people from Inria. I will have to change the list. Here from Inria, there is also Marc-Olivier Renaud, who is a researcher at Inria, close to here. He couldn't be attended the meeting today, these 2 days. And I will explain the team in which he's involved. He's a new member of Links since last year. And someone from outside the partners of the Links, Michel Barbeau from Carleton, Ottawa, who was invited researcher by Joaquin Garcia Alfaro in the last years, and we see him several times. Okay, so I need to talk about to explain what is Quantum 2.0, but I first need to speak about the first revolution, quantum revolution, the Quantum 1.0, for information, communication, and the communication technology. Links is the Laboratory of Information Networking and Communication, so it's about ICT. So Quantum has some aspect that is involved in ICT research. So the Quantum 1.0 is about the manipulation of assemble of atoms, of particles, photons, electrons. This revolution started just after the Second World War. For example, with the invention of the maser and laser, microwave amplified, I do not remember. Sorry, the laser is an acronym for light amplification, and M is microwave instead of light. It was invented in the 50s. Here I just represent a photo from 2 researchers from the Bell Labs at that time who work on this in this research. And you have also the inversion, for example, of the transistor at here again at Bell Labs, and which involves also quantum physics. But these two invention, it's not individual particles. It is a collective set of a collection of particles that work together. And we usually today we use it these technologies to as they are commercially available for decades now, and it is really involved, and we do not matter too much about them in our world. Quantum 2.0 is something a bit different. It's the manipulation of individual particles, photons, electrons, and the most known application is quantum computing. Computers. You have a picture of the quantum computer by IBM. There are also other technologies that are developed in Europe and in France, in particular, close to here in Massy. You have the quantum computer from Pascal here. And in Nokia Bell Labs, so it's not in France, but in the US, there are some people working on some specific qubits, topological qubits in their lab. The research domain concerned by Quantum 2.0 is first quantum computing and algorithms to give quantum advantage compared to classical computing. You have the Shor's algorithms, which is about integer factorization, and with that it's an exponential speedup compared to classical algorithms. There is a threat by quantum computers to break RSA algorithms for security, for encryption, when the quantum computer will be efficient enough. You have other algorithms like Rover with quadratic speedup for the search in a database. And you can also have quantum version of optimization algorithms and machine learning algorithms. You also have distributed quantum algorithms that are interesting for quantum networks that I will talk later, such as the quantum version of Byzantine agreement, which can be run in a constant number of steps of communication instead of something that is linear with n or almost linear with a square root of n, depending on the version of the algorithms, classical algorithms. You have quantum communication for quantum safe communications. First way to be quantum safe could be post-quantum cryptography. They are in fact not quantum; they are classical systems that are secure until they are not broken. They are classical. There are no strict proof theoretically that they are safe. But you have another way to fight against Shor's algorithms, for example, is quantum key distribution systems that are secured by the quantum physical laws. They are commercially available today for point-to-point, but we need to, if one wants to increase the distance, we need to do other things like quantum networks. And I will talk about this later. So quantum networks is a certain aspect. We use quantum repeaters to increase the distance of entanglement sharing between remote nodes. And this can be used for quantum key distribution to increase the distance, but also to have other applications such as distributed quantum computing, blind computing, and other things. Quantum network is a distributed system that creates entangled pairs of qubits, Bell pairs, between any pair of nodes in a network. And you have also other applications such as quantum sensing, but I put them in gray here. It is not related with what we do at Links. So what is done here at Links and who? On quantum algorithms, you have Joaquin Garcia Alfaro, not Alvaro like it is written here. I see it's not the last presentation I put on the website. With a PhD student, Jan Burge. You will have a poster and a presentation by Jan today. You have quantum distributed algorithms. So Marc-Olivier Renou is a researcher in the area who is working on it. He has a full team with postdoc, other members, permanent members, postdoc, and PhD students. He co-advised with us, so Rémi Varlot and myself, two PhD students, Luis Muñecas Thomas, you will have a present poster by him today, and Amanda Way, who unfortunately couldn't attend, is not present in France this week. In Sorbonne, we have some regular meeting with Sorbonne University on the quantum distributed algorithms. With Sébastien Tixoy, who brought his experience on and competencies on distributed systems and algorithms. And on quantum networks, so it's a topic that we work on at Nokia Bell Labs with Rémi and myself. We have an intern, Anna, who is also here today, and there is, she has a poster that we will present today. And Telecom Sud Paris, you have Joaquin Garcia Alfaro, again, it's copy and paste. And with, as visitor, Michel Barbeau from Carleton, PhD student Jan Burge, and also an intern, Caio Escorcio. There are other topics for additional collaboration about quantum information, the quantum version of information theory in general. There are things that still can be done, and we could do things on this topic. There are classical network tools that can be adapted to quantum networks. Queuing theory, you will see an application in the next slide. Network coding, there are quantum version of network coding, which is quite funny to work with it. I put a question mark here, network calculus. And there is someone that I didn't yet mention, Anne Bouillard, who is a member at Links from École Normale Supérieure associated with INRIA. And we already had a discussion with her about queuing theory and what we do in terms of queuing theory and for quantum networks. And maybe we will see if we can do things about a quantum version for network calculus that could be interesting also. There is the notion of quantum graph states that are really interesting in quantum distributed systems. And there may be some links with classical graph theory that could be done and that are not yet be done. And maybe there are other topics also. And for quantum distributed system, I already talk about distributed quantum algorithms. There are many versions of Byzantine agreement, and we may see how to adapt them in quantum. There are some local models also, and so on. And maybe others. So for the moment, there are some activities, but there is room for additional activities on this topic in terms of collaboration at Links. So I will first talk about research on quantum algorithms that is mainly carried out at Links at Telecom Sud Paris with Jan Burge, the PhD student of Joaquin. When he was doing his master, he developed a version of the Shapley value method that is something that allow to evaluate to share how to say. It is in game theory. In game theory, you can have some coalition, and if the coalition that has been made won, you need to share the gain, and there is a fair way to share the gain. That is the Shapley value method. It is fair in the sense that it respects. I do not describe here the other properties. There are some required properties that are enabled by the Shapley value and that are good in terms of fairness in the sharing of the gain for the coalition. And this is something that really can be useful to work on quantum explainable AI. This is something that Yain did during his master, and they can be used in many other purposes. And one of the thing that one of the topics in which he will try to use this method is to identify the critical node in quantum networks in terms of security of the quantum networks and the vulnerability of the nodes, to evaluate how the network is vulnerable for each node in the quantum network. And there is a publication here. He is also working on quantum support vector machine, and I will let him explain it. It will be in the next presentation. More detail in Jan Burge's presentation. The team that is involved in on the Quantum 2.0 at Ineria is the team Ficus that has been created and which is managed by Marc-Olivier Renou at Ineria. This is a joint project team between Ineria and École Polytechnique, some department at École Polytechnique. It's about information theory, physics, and quantum simulation. There are currently 3 permanent researchers, including Marc-Olivier, who is a member at Links, was been member at Links since last year. There are 6 postdocs and 10 PhD students. Among the 10, there are the 2 PhD students that we are co-advising with him. The topic that is involved in at Links is the quantum information theory that try to exploit the opportunities that are brought by quantum physics and quantum information processing in quantum networks and distributed quantum computing. It is about looking at the quantum correlation, the distributed computing in networks, the foundation of quantum theory, certification of quantum devices. It is something that is really interesting for us. We are working on quantum networks, and we want to certify that the quantum network is doing the right thing, what is expected. Yeah. There are 2 other topics, but they are not involved in at Links, machine learning for quantum science and some categorical and graphical frameworks for quantum computing. In terms of research on distributed quantum algorithms for quantum networks, it's a joint work between Ineria and Nokia Bell Labs. We have 2 PhD students, Luis Municas Thomas will show you with his poster the certification of quantum network systems. There's many things. It is based on self-testing, so what you will show more precisely is self-testing of specific quantum system, fermionic systems, you will see with him. But in the next phase, we will work together with Marc-Olivier, Luis, and myself on the self-testing for quantum network certification to answer the question, does the quantum networks deliver what he should deliver? So you will add more detail on the poster of Luis Municas Thomas. There is another PhD student, Amanda Way, who is working on cooperative quantum gains with limited communication. There is also a collaboration on distributed quantum system that is larger than what we are doing with these 2 PhD studies. We have, as I said, we have discussion with Sebastian Tixes about the quantum version of Byzantine agreement, which is one family of distributed quantum algorithms in which the quantum version brings some advantages. We had a workshop at Alto, so it was a joint workshop between Alto, Ineria, and Nokia Bell Labs in October. So you have the link here. And so after this workshop, we decided to build a new European project in the Cantera framework, which is called the Quantum Network Algorithm. So it has been accepted, and we should start in October this year. And it is with Jukka Suomela at Alto, Marc-Olivier Renou at Ineria, and myself and Nokia Bell Labs, plus other people from other institutions in Europe. So about quantum networks. So the definition I already give it. It's a distributed system to distributed entanglement between nodes, Bell pairs. A Bell pair is a maximally entangled pair of qubits. It can be seen as a correlation, a quantum correlation, and it is a new resource. So quantum networks will not replace the classical networks, but it will give a new resource that can be exploited to do things that classical networks cannot do. In terms of quantum link realization, to explain what we do after, there are 3 ways to realize quantum links. The first one is to have a source of Bell state, a pair of a source of Bell state as a pair of photons that are entangled together, maximally entangled. Each photon goes one node, and there is one photon that goes on the right and one photon that goes on the left. Then they are transduced meaning that the photon, the qubit that was carried by the photon is transferred into a matter qubit through the transduction process, will be stored in quantum memories. This is the first, so mid-link source to transduction. You can have one source, one transduction. The source here is a bit different. Instead of having two photons that are entangled, you have also possibilities to have create entanglement between a qubit in a quantum memory, matter qubit, and a qubit on a photon, flying qubit. So you have you have a source on one side of the link. The qubit, the matter qubit is stored in the quantum memory, and the photon is flying towards the other node, in which you have a transduction process to transform it into a matter qubit. The third one is to have two source matter flying qubit on each side. One of the qubits is stored locally, and the other is going through the link. In the middle, somewhere in the middle of the link, the two photons interfered with an optical interferometer, which is like processing a partial Bell state measurement. Two bits are measured and sent towards the two nodes. And by doing that, at the end, the two nodes know they have a Bell pair between the qubits they shared, one qubit on each side. And this can be used later to proceed quantum correlation, quantum entanglement in the network. So that's the three ways. There might be other ones, but you see there are many ways to process. And then if one you have that, so here I present three links. I present with the first way to realize the link. I just check the time. But you can replace the quantum link with a source in the middle, but the two other things, it will work similarly. What is important is that each link creates a Bell pair between adjacent nodes here. And in an intermediate node that I call quantum router here, left or right, quantum router or quantum repeater. So you have qubits that are stored in two quantum buffers, one coming from a Bell pair from the left and one coming from the Bell pair from the right. And you proceed to what is called quantum stitching or I wrote quantum stitching, entanglement stitching. It is also called entanglement swapping. So it's some quantum processing and measurement. There are two bits that are measured that are sent towards the end nodes A and B. This is what we call consolidation. And after all this process made in the middle, the node A and B will know that they will share a given Bell pair. It can be there are several Bell pairs, but knowing the bits that they receive from the consolidation process, they will know which Bell pair they will have. And then this Bell pair can be consumed by the quantum application later. So we are working on, so I will speed up a bit now. We are working on the layer of the quantum network protocol stack, the different layers. As you see, it looks a bit like classical networks. You have physical, link, network, session, service, and application layer. But there are some quantum specificities to be taken into account in the design of these layers. So for the physical layer, you have all the quantum physical process I talked about previously. In the link layer, what you will have, there are some losses in the fiber. And because of the losses, the loss in the fiber, you need to know if the photon has been lost or not, and to take this into account. And there are some ways to know it. And but you need to have some acknowledgement between the two end nodes to know if the qubit have been successfully stored in the quantum memories. This is the acknowledgement, so it is called heralding. And we had another thing that we designed for the quantum link with Remy is the throttling of the rate to because of the loss you have a lot of variations in terms of you have a given rate, but there are a lot of jitters, and so a lot of variation in the rate at short distance, at short time scale because of this loss. And we need the throttling is there to decrease this jitter. The network layer, we have a path assignment, which correspond to switching, entanglement stitching, and consolidation. In the session layer, we will proceed to error correction and there, what we call a Bell state purification, which is something that is a bit like quantum error correction, but adapted to Bell pairs, because we know that we should share Bell pairs, but there may be some errors, and so there are some other ways to correct this kind of error. At the service layer, we will have service that is adapted to the various quantum application, and then you have the application layer, which is the client application. From physical to session layer, everything will be done inside the network, while for the service layer and the application layer, it will be something that is more specific to the application, then it will be inside the client layer, the client application. So with Remy, we work together on this structuration of the layers for the quantum networks. We also work on the link layer. So here I represent the link. You have the link that delivers some Bell pairs, but because of the loss. So the link creates a Bell pair at a given rate. But there are some losses, but the losses are heralded. And so you may have the Bell pair will be possible to be used in the upper layer if it has been well stored on both sides. And this is now with acknowledgement from between the two nodes. So the qubits need to be stored, waiting for the acknowledgement from the other part. This is why we need quantum buffers. If the acknowledgement is positive, the Bell pair will be released. If it is negative, then if one qubit is stored, but the other has been lost on the other side, the qubit that was stored on one side will be discarded. And so we need, so as I said, we need quantum buffers. And there is the impact of loss. If we consider 50 kilometers of classical standard fiber, it is 90% of loss. So very large number of photons will be, and qubits will be lost. And it is completely random. So this will induce high jitter if you do nothing. So what we propose is a scheme to reduce this jitter. And how we do it, we simply add an additional buffer, small buffer, after the acknowledgement buffer that will of a fixed size, and that will, and the delivery of the rate will be throttled, meaning that the rate at which the Bell pairs will deliver will be lower than the average rate at which they are received. So most of the time the buffer will be full. So there are some qubits that could be used, but the buffer is full, and so it will be this qubit will be discarded. And for the release, the probability that the buffer is empty will be very low, epsilon, and this will be it was here, and this so by tuning the rate of the throttling, by tuning the throttling ratio, the rate at which the Bell pair will be delivered, we can decrease epsilon as low as we would like. So we did, I will go fast on it. We did some modeling with Markov chain of this system. We solved the Markov chain using a Python program, and here is the kind of outcomes, the results that we obtained. We see that if we increase the size of the buffer, but it's few qubits, it's not a big buffers, we can decrease a lot the probability of failure or delivery failure, the epsilon I was talking about before. And also, if we decrease the ratio of throttling, we also decrease this failure probability. And for example, if with 90% quantum link losses, you can reach a probability failure of about 10 to the -4 with a buffer of size 10 qubits and a throttling ratio of 70%. Without throttling, if the throttling ratio was 100%, it will be the 5% probability of failure. So this we submitted the paper at the ECOC conference, and it has been accepted. It will be presented in September this year. We also developed, I will go fast because the time is running. We also developed a simulator to test our protocol that we designed with Remy, and we use it also for demo. Here I will go fast because you will have a poster from Anna on it, our intern. We try to optimize the end-to-end quantum path with intermediate quantum repeaters. We have different parameters that you can tune, and we try to get the best performances. And to end, we have some collaboration with Telecom Sud Paris and Nokia on quantum network and security. So I will go fast on this part because Jan Birch will present it after me. He used the quantum algorithm I was talking about before in the beginning of my this presentation in the context of the security of quantum networks. And there is a collaboration that has started between Telecom Sud Paris and Nokia. For example, I participate to the jury of the thesis of Jan Birch, of the first year thesis follow-up of Jan Birch last month. We had many discussions. We have a brainstorming meeting last month also. And Anna, who is intern with us, should be hired as research engineer by Telecom Sud Paris to work on quantum security. And we will go on working together with Anna at Telecom Sud Paris, if everything goes well, beginning of this, in the next autumn. And this may be followed by a PhD thesis after for her. And that's it. Quantum 2.0 is the emergence of quantum ICT, which should be looked at LINX because LINX is about ICT. And we carry out several research, and there may be new research in the future on this topic. Thank you very much.